So that's everything in the Vector2 type. The Vector3 type, of course, has an extra z component. It has a third float. And so we have these two more static properties, forward and back. Forward is the unit vector pointing down the z-axis in the positive direction, and back is the unit vector pointing in the negative direction down the z-axis. Then Vector3 has several methods which Vector2 doesn't, and I'm not sure why that's the case, because I can imagine scenarios where you'd want to do these things on Vector2s as well. Though the fact that Vector2 doesn't have these methods isn't really a big hindrance, because we can always just take our Vector2 values and get their Vector3 equivalent, where it's the same values, except of course the z component is 0, and then use these methods to get our results and just convert back to Vector2. So it's not much of a hindrance that Vector2 doesn't have these, but it is still just a little strange. I'm not sure what the rationale for that was. Anyway, so the first of these, orthonormalize, has two overloads, one taking 2 vectors and one taking 3, and all these vector arguments are passed by reference. Orthonormalize doesn't return anything, it's modifying the vectors that you pass in. And here looking at the first overload, what it does to A, the first argument, is it simply normalizes it, but then the second vector, it wants to make that a unit vector that is perpendicular to A. And of course, given a vector, there is a full 360 degrees of possible vectors that are perpendicular to it. And so the question is, well, which unit vector does B become? Well, what it does is it takes whatever the input vector B is, and between A and B, that forms a plane, and you can imagine B being swung on that plane until it is perpendicular with A. And that's what orthonormalize does. Given 2 vectors, we want to tweak them until they're unit vectors that are perpendicular to each other. A doesn't move, B is adjusted to be perpendicular to A. The second overload does the same thing, but then for C, the third vector argument, orthonormalize will mutate this into a unit vector that's perpendicular to both A and B. So this is like adding in a third perpendicular axis. Adding in a unit vector that's perpendicular to both of those, well, there's 2 possible choices. And of course, those 2 vectors go in opposite directions. So the question is, well, which of those 2 possibilities will orthonormalize choose? And that is determined by, for whatever your input vector is, vectors A and B form a plane, and C is either pointing to one side of that plane or the other. And that determines which of the 2 unit vectors perpendicular to A and B that C will become. And actually also this is the case where C is already on the plane of A and B, so I don't know how it breaks the tie in that case. It has to break it in one way or the other, so the algorithm probably just picks one of the 2. Next we have the project method, and here you should think of the vector B as being more like a ray. So it's describing a direction, but imagine it not really having a magnitude, it just goes off into infinity. And the vector that project returns is the point along that ray of B, which A is closest to. A describes a point, and somewhere along the ray of B, there's a point which A is closest to. Another way to think of it is, again, imagine B is more like a ray going off into infinity, but it forms a right triangle with A, and project will return for that right triangle, it returns the length of the vector along B that forms that right triangle. It returns a so-called adjacent of that right triangle. And then we have project on plane, which does something very similar, except instead of projecting A onto the ray described by B, it projects A onto the line perpendicular to B. So it's returning the point on that line perpendicular to B, which A is closest to. The formula for this is actually very simple. You simply project A onto B and subtract the result of that from A, and that gets us the result of project on plane. Here's a little illustration of the project method. We have our vectors A and B, and we're projecting A onto B, and then we're going to draw A is green, B is yellow, and the projection vector will make black. Come over here, play the game, maximize this. So here's our vector A in green, our vector B in yellow, and if we project A onto B, there's a right triangle formed between them, and when you form the right triangle between them, this is where the so-called adjacent of that right triangle ends. Or another way to think of it, the closest point on the line described by B, the closest point to vector A, this point over here, is this one right here where the black line ends. And actually, I really shouldn't have said that we project onto a ray of B. It's always a line, because as we can see here, if I were to change A and make this -2, come back here, So now imagine B is a line extending off in both directions into infinity, and so the closest point here of A on that line of B is right here. In fact, just be clear, it really doesn't matter what the magnitude of B is. If we normalize this, or just here, I'm just going to divide it by some random number to make it much smaller. If we do that, come back, wait for the code to recompile, doesn't change the projection whatsoever. So the length of the B vector we're projecting onto, its magnitude, does not matter. Now instead of project, let's use project on plane, drawing A as green, B as yellow, and the projection vector as black. Let's see what that gets us. Here's our A vector, here's B, and again, the magnitude of B really doesn't matter. All it's used for in this case is to describe a line running perpendicular to it, so it would be a line running this way. And what we want to find is the point along that line which A is closest to. And as you can see, that's right here. Though another way to think of it is that we're forming a right triangle, and so the vector we get back from the method is actually the adjacent of that right triangle. It's just in this case, it's a right triangle formed between A and the line perpendicular to B rather than B itself. So that's both project and project on plane. And just understand, I've demonstrated them in 2 dimensions on the XY plane, but we can use any 3-dimensional vectors. So here, let me just quickly demonstrate that. I will give this a z-coordinate of 4. And we come back, wait for the update, for the code to recompile, and, well, it doesn't seem to have changed, but that's just because of our orthographic perspective. If I switch out to perspective mode, you can see here that now that vector is going back into the z distance. And so what the method does is that for the plane formed by A and B, it finds the line perpendicular to B on that plane, and that is what is projecting A onto. Next on Vector3, we have slurp and slurp unclamped. These are much like lerp and lerp unclamped, which we saw in Vector2. Vector3 has those as well, but in addition it has these two, slurp and slurp unclamped. And the difference is that here we are spherically linearly interpolating, rather than just linearly interpolating. And what that means is that we are interpolating a position in between A and B. We're going from A towards B, in this case 40% of the way, but instead of going directly, it's as if we're moving along the surface of a sphere, hence the name spherically linearly interpolating. Except because A and B aren't necessarily the same magnitude, I think it might be more accurate to think of this as a method that linearly interpolates the angle of movement from A to B rather than the absolute position of A and B. It's probably just easier to illustrate this in code. So here we have our vectors A and B, and we're going to draw the first one as a green line, the second as a red. And then we're going to draw 3 slurps from A to B, first 25% of the way from A to B, then 50%, and then 75%, and we'll make those blue. And then we'll do the same thing with lerp, but make those magenta. And because both of these vectors, just for simplicity of demonstration, I made them both on the XY plane, they both have z components of 0. When we go back to Unity, I'm going to want to fix my axis, so we're looking at the XY plane, orthographic projection, expand this, and then hit play. Okay. So green, this is the A vector, the red vector is B, and then if we linearly interpolate between the position of A and B, this is 25% of the way, this is 50% of the way, this is 75% of the way. But when we spherically linearly interpolate, this vector here is a vector where the full angle between A and B, this is 25% of that angle, this is 50% of that angle, and this is 75% of that angle. And it turns out that, well, halfway, our lerp and our slurp are going to have the same direction vectors, but that's not the case at other points along the way from A to B. And understand the magnitude of our slurp vectors, the blue vectors here, that is determined by linearly interpolating between the magnitude of A and B. But in this case, I made their magnitudes the same, so the magnitude isn't changing. In this case, it really looks like a spherical linear interpolation. It's as if we're moving along the surface of a sphere, or rather in 2 dimensions along the surface of a circle. But if I come back here, I'm going to make this shorter. Same direction, just shorter. Divided everything by 2. Wait for the recompile. And then, okay, yeah. So the linear interpolation part, that makes sense. It's just the points again, 25%, 50%, and 75% of the way from A to B. But now our slurp vectors, the angles haven't changed. Their directions are the same. But the magnitude of these vectors, this one is 25% in between the magnitude of A and B. This is 50% in between the magnitude of A and B. And this is 75% of the magnitude from A to B. And just to illustrate again that this can work in 3 dimensions, here I'll give this a z component of 7, save that code, go back here, wait for the recompile, and now we actually get different results, and that's actually apparent in the orthographic projection. But here I'll switch to perspective view, come here and rotate. So the way to think of it is that A and B form a plane, and for slurp, we are linearly interpolating the angle between A and B. So this first vector over here, the angle between it and A is 25% of the angle between B and A. And again, the magnitude is linearly interpolated to be 25% of the way from A to B. And I believe in this case, A would be a longer vector. Here, let me make that even more apparent. I will make this a big number, and we'll just move over a little bit. Wait for the recompile, and yeah, so now A is definitely bigger than B, and so when we linearly interpolate 25% of the way from A to B, the magnitude is actually being shrunk as we get closer to B. As for slurp unclamped, in that case, our percentage value is not clamped into the range of 0 to 1, so we can have like 1.25, 1.5, 1.75, etc. And we'll draw these in black, and let's see what that looks like here. And there, so this is 125% of the way from A to B. This is 150, 175, 200%, 225, 250. And notice in this case, because A is longer than B, the magnitude is getting shorter and shorter. And in fact, eventually our unclamped slurp vectors are going to go negative. In fact, I can illustrate this if here I'll just make this z component larger. So now vector A has a significantly larger magnitude than B. Come back here, wait for the code to recompile. And okay, well, here's 1.25, here's 1.5, and here's, you expect the angle to be right here, and it is, but now our magnitude has gone negative, so it's now going off into the other direction. So just watch out for that. It can be a little confusing. We have another method, rotate towards, which is like slurp, but here the third argument is not a percentage of travel from A to B. It's rather the amount we want to travel in terms of absolute radians. So we're still finding a vector that is swung from A to B, but we're specifying in radians the actual angular distance we want to go. And in the event this angle is larger than the angle between A and B, well, what we get back is a vector with the same direction as B. It won't overshoot. So in a sense, the rotation, the movement is clamped by B itself. And then this fourth argument is specifying how much we want the magnitude to change. Like say here, imagine A has a magnitude of 5 and B has a magnitude of 10. Well, the vector returned by rotate towards should have a magnitude closer to B. How much closer? Well, 2 units closer. So the returned vector's magnitude would be 7 in that case. Though if the difference in magnitude between A and B were less than this distance, the returned vector would just have the magnitude of B itself. So it's possible we specify values large enough for both these arguments where the vector we get back is just equal to B. And somewhat unfortunately, the documentation says something about linearly interpolating the magnitude, but in all my tests, I didn't see that behavior at all. It seems to always return a vector where this is the change in magnitude. This is the delta magnitude, but it's capped at the magnitude of B, so we're never going to overshoot B. As far as I can tell, that's the real behavior, and there's no actual linear interpolation between the magnitude. And so whatever the angle it is we specify, that has no bearing on the magnitude of the return vector. Only the last argument has an effect on that. Lastly, we have the cross method, which gets us the cross product of 2 vectors. And this is the one method that doesn't apply to vector 2s. It's something that doesn't make sense in 2 dimensions, because what it returns, effectively, is a vector that is perpendicular to both A and B. And the way you compute that is that, well, for the x component, that's found with these operations, which note don't involve the x components of either A or B. And then when you find the y components, it's these operations, which note don't involve the y components of A or B. And then to find the z component, similar deal, except again, it doesn't involve the z components of either A or B. Anyway, we won't go through the proof here, but this gets us back a vector which is perpendicular to both A and B. And the question is, well, which way does it go? Given 2 vectors, the third vector that's perpendicular to them goes in one of 2 directions. And so which way does it face? Well, the way this is computed effectively gives us the cross product according to the left-handed rule. So if you hold up your left hand and form an L with your thumb and index finger and stick out your middle finger away from them, it's like your hand is representing 3 perpendicular axes. Well, your thumb would be the A vector, your index finger would be B, and your middle finger is the cross product. If you made the same gesture with your right hand, where A is your thumb and B is your index finger, your middle finger would in a sense be oriented in the opposite direction. So that's the distinction between left hand and right hand systems. So when we have 3 axes, we talk about left-handed systems and right-handed systems. Anyway, so that explains the direction, but what about the magnitude? Well, it turns out the magnitude of the cross product, again, we won't prove this, but it turns out to be equal to the magnitude of A and B multiplied together with also the sine of the angle between them. And like with the dot product, this equation can come in useful in certain circumstances we won't go into here. Let's though just see a demonstration of getting the cross product. Here we have A and B. I'm drawing A as green, B as red, and I'm computing the cross product manually and then drawing that as a yellow line. But then I'm also computing the cross product using the built-in method, and we should see the same result, but I'm drawing that as a black line on top of our yellow line, but normalized, so it should be much shorter. Otherwise, we wouldn't see the yellow line at all. And lastly here, I'm getting the cross product of this time B and A. I've reversed the order, because cross product, unlike dot product, is not commutative. The order matters. And what that changes is it flips the direction of the cross product vector. The left hand rule still applies. Form 3 perpendicular axes in your left hand with your thumb, index finger, and middle finger. But in this case, now B is your thumb, A is your index finger, and so now the cross product is going in the other way than if we got the cross product of A and B. So let's see this in Unity. There. So we have our 2 original vectors. A is green, B is red. Yellow is the cross product with the full magnitude, but then if we normalize it, we get this little black line, and the cayenne line is the cross product of B and A, also normalized. And notice it's just the inverse direction from the cross product of A and B.